All right, let's talk about something that's literally everywhere, but kind of hidden in plain sight, the Matrix. Now, I know they can seem a little intimidating, but they are the absolute building blocks of our digital world. I mean, everything from the screen on your phone to the mind-blowing graphics in a video game. So let's dive in and see how these simple grids power our incredibly complex world.
So let's just think for a second. Imagine you're building a massive digital universe for a game, or maybe you're a scientist trying to make sense of millions of data points. What's the very first and biggest problem you're going to face? How do you organize all of that information? How do you give every single piece a specific place and a set of rules to follow?
Well, the answer is surprisingly simple and kind of beautiful. You do it with a grid of numbers. And this grid, this little rectangular box of information, that is a matrix. It's the cleanest, most powerful way to organize data, and it is the foundation for absolutely everything we're about to get into.
Okay, so let's start at square one. To really get a grip on how powerful these things are, we've got to answer the most basic question of all. What exactly is a matrix?
At its absolute core, a matrix is just a box of numbers. They're called elements, and they're just arranged in a certain number of rows, we call that M, and a certain number of columns, we call that N. The key thing here is that every single number has its own unique address, defined by its row and column. Think of it like a perfectly organized filing cabinet, but for numbers.
Right, but here's the thing. Not all matrices are the same, not even close. In fact, there are tons of different types, and each one has its own special properties and its own job to do. So to make sense of it all, let's take a quick trip to the Matrix Zoo and meet some of the most common species you'll run into. First up, you've got the basic shapes. There's your row matrix, which, you guessed it, is just one single row, and its counterpart, the column matrix. Then you've got the really important one, the square matrix, where the number of rows equals the number of columns. You'll see this one all the time. And finally, you have the null matrix, where every single element inside is just zero. Simple, right? But they're all essential.
Now check these two out. They're basically cousins. On the left, we've got a diagonal matrix. See how the only non-zero numbers are sitting on that main diagonal line, running from the top left to the bottom right? Okay, now look to the right. That's an identity matrix. It's a special kind of diagonal matrix where all those numbers on the diagonal are specifically the number 1. You have to remember this one. It's like the number 1 of the matrix world. It's a fundamental benchmark, and it's hugely important. Now for two really special types. On the left, we have a symmetric matrix. It's a perfect mirror image of itself across that main diagonal. The top right corner is exactly the same as the bottom left. Then, on the right, you've got its spooky twin, a skew-symmetric matrix. It's an anti-mirror, where the reflection is the negative of the original number. And notice that key detail. A skew-symmetric matrix has to have zeros on its main diagonal. Remember these two, the mirror and the anti-mirror, because they are the stars of our final trick.
So, we know what they are, we've met the different types. Now what can we actually do with them? Well, it's time to talk about the basic rules of matrix arithmetic. Matrix addition is about as easy as it gets. Seriously, you just take two matrices that are the exact same size, that's the one and only rule, and you add the numbers that are in the corresponding positions. Top left adds to top left, bottom right to bottom right, and so on. Easy peasy. Multiplication, on the other hand, is where things get a bit more interesting and a lot more powerful. There's one golden rule you can absolutely never break. The number of columns in the first matrix must be equal to the number of rows in the second. If they don't match, you just can't multiply them. It's a no-go. For example, here are two matrices, A and B, that follow the rule. We can multiply them. We do the calculation, and we get this resulting matrix here. Seems straightforward enough, right? But hold on a second. In regular math, 5 times 4 is the same as 4 times 5. The order doesn't matter. So if that's what A times B looks like, what do you think B times A is going to look like?
Surprise! It's a completely different matrix. And this is a mind-bendingly important concept. For matrices, A times B is not the same as B times A. This property, called non-commutativity, isn't a flaw, it's a feature. It's what makes 3D computer graphics possible. I mean, think about it. Rotating a character and then moving it forward is very different from moving it forward and then rotating it. The order matters, and matrices capture that perfectly.
Okay, so if we can add and multiply, how do we divide?
Well, in the matrix world, we don't really divide. Instead, we use something way more powerful, the inverse. The inverse of a matrix A
which we write as a to the power of -1, is the special matrix that essentially undoes A. When you multiply a matrix by its own inverse, you get right back to that clean, simple identity matrix we saw earlier. But there is a catch. Not every matrix has an inverse. To have one, a matrix has to be square, and it has to have something called a non-zero determinant. If that determinant is 0, no inverse exists.
Now, the process for actually finding the inverse can look a little intimidating, but it's really just a 4-step recipe. First, you calculate one single number called the determinant. That tells you if an inverse even exists. Then, you do some calculations to create a matrix of cofactors. After that, you rearrange that to get something called the adjoint matrix, and finally, you take that adjoint matrix and divide it by the determinant from step 1. That gives you the inverse.
And here is that whole 4-step recipe captured in one single formula. The inverse of A is equal to 1 divided by its determinant, multiplied by that special adjoint matrix. This one elegant equation just packages that entire process together.
All right, we've covered the types, the arithmetic, and the inverse. Now it's time to put it all together for one final, very cool matrix trick.
So there's a theorem that sounds almost like a riddle. It states that any square matrix, no matter how random or messy it looks, can be broken down into the sum of a perfectly symmetric matrix and a perfectly skew-symmetric matrix. It's like discovering that every rock has a perfect crystal and its exact opposite hidden inside.
And how do you perform this little bit of magic? With this beautifully simple formula right here. You just take the matrix and its transpose. That's the matrix just flipped across its diagonal, and you add them together. Then you do the same thing again, but you subtract them. The formula combines these two results to perfectly separate the symmetric and skew-symmetric parts. And here's the result. On the left is our original random-looking matrix A, and after we apply that formula, it's been perfectly split into the two matrices on the right. The first part is perfectly symmetric, a perfect mirror image across the diagonal. The second is perfectly skew-symmetric, that anti-mirror with all zeros on the diagonal. Ta-da!
So we've seen that a matrix isn't just some boring grid of numbers. It's a powerful tool for organizing information, it's a language for describing transformations, and it even contains its own hidden, perfectly balanced internal structure. And that leaves you with a final thought. If a simple grid can create and define entire worlds, what other complex systems are out there just waiting for the right framework to organize them?